Hi, thanks for joining me today for our discussion on the use of diesel engines in power generation, specifically fuel problems and treatment options for power generation diesel engines. I am Eric Bjornstad, and I'm the Technical Information Director for Bell Performance here in Central Florida. And so today, in our time together, what we want to do is we want to touch on all things having to do with power generation diesel engines, diesel internal combustion engines. So we talk about the problems that these engines have, both before combustion, during combustion, and post-combustion. We want to talk about what causes, what helps contribute as causal factors to those problems. And then after we talk about that, it's of course only fitting that if we're going to talk about problems, then we should also examine some of the best practice solutions that have been shown to solve those problems. And we will also try and touch on the nuance of what you should be looking for, or what the characteristics of the best solution really are. So to start with, in order to understand the problems, the fuel-related problems that power generation internal combustion engines have, we have to start at the beginning by looking at the fuel itself. Now, the catalytic cracking processes that have been instituted really by necessity in the last few decades, those have, on the good side, those have really enabled refineries to take out significantly more distillate fuel out of each barrel of crude. Distillate fuel is the stuff like number 2 diesel and on-road gasoline, and the more of that they can get out of each barrel of crude, the more profitable their business is going to be. Now, historically, if you see by the graphic, they would typically get, let's say if you go back to the early 1970s, they might get out of each barrel of crude, they might get 65% of it would be distillate fuel, and the remaining 35% would be the residual, which the residual includes heavy fuel oil. But because they have instituted all these cracking processes, they're getting a lot more distillate fuel out of it. They're getting 90% these days, sometimes even as high as 93%, which means that only 7 to 10% of the crude oil volume, as opposed to 35%, only 7 to 10% today is the residual that they get out of each barrel of crude. And this pretty dramatic change impacts the characteristics and also the properties of this kind of fuel. Now, residual heavy fuel oil, residual heavy fuel is used in both boiler furnace applications and also in internal combustion engine power generation applications as well. Now, there are different kinds of engines that are used across the board. And they're delineated by their speed. You have high-speed engines, which are ones that are above 1,000 RPMs, and those predominantly are the ones that you find on small generators and also on diesel vehicles. Medium-speed engines are 300 to 1,000 RPM, and those are what you typically find in large electrical generators. But the one that's of particular interest to us today are the large, low-speed diesel engines. They're the ones that tend to be heaviest, and so because they are the heaviest, that means that they're more likely to be used in places where weight does not matter nearly as much. Like, for example, on large marine ships, where weight isn't really that much of a factor because of the nature of what marine ships are. So for our purposes, we are most interested in the larger low-speed diesel engines, and these diesel engines tend to burn heavy fuel oil. The HFO is a choice for both low-speed and also a lot of medium-speed generation systems. For the high-speed ones, remember, you're talking about small generators and also vehicles. Those are the ones that use the distillate, the number 2, like the on-road and off-road number 2 diesel fuel oils. Now, HFO, the reason why the large and medium speed engines use HFO is, number one, it's cheap, low cost, And second of all, the larger engines can be engineered to better be able to handle the larger amount of impurities that this HFO, this residual HFO, inherently brings along with it. And by impurities, we're talking about metallic and inorganic content, and also higher sulfur content. And so, you know, these are the characteristics of what this HFO brings along with it. It's cheap. It's got higher sulfur content and lower lubricity. The higher sulfur content comes because of the fact that it is a residual fuel. They want to keep the sulfur out of the distillate stuff, and so it tends to get concentrated more in the residual fuels. Same thing for the metallics. They cannot have metallic content like iron or aluminum or silicon in distillate diesel fuels. So all of that, which was present to begin with in the crude oil, where's it going to end up? It's going to end up in the residual HFO. Now, there's a lot of facilities generating diesel gensets. These kind of diesel gensets are used in a variety of places across the marketplace, and you can see some of them spelled out here. You've got hospitals, office and commercial complexes that have to generate power or have emergency backup power. That's another thing. Hotels, they're used in oil exploration and also in mines. And so the reason why we bring this up is because we need to consider how any particular fuel-related problems might affect these specific kinds of businesses. What are their specific pain points? What are their specific concerns that they might have in their specific line of work? Well, because HFO, heavy fuel oil from secondary refining products of crude oil, the residual leftover stuff, HFO can tend to be prone to a number of different issues, both pre-combustion, during combustion, and post-combustion. And if you've been in the power gen industry, or if you've been in an industry that uses this kind of fuel and the lower medium speed engines, we're not telling you something that you don't already know. This is probably old news to you. So touching on some of these problems just very briefly, one problem is that they can tend to be prone to sludge formation. Sludge formation in the storage tanks, because residual fuel can have a tendency, because it has a very high asphaltene content, if you leave it sitting for an appreciable amount of time, that those larger heavy ends will tend to settle out in the storage tanks. You can get filter blocking. You can get, of course, some of these fuels have to be centrifuged to get the impurities out, and so you have that aspect of it. You can have poor atomization of the fuel. That influences how well it's going to burn, is how well it atomizes. And, of course, poor ignition and combustion properties. All can be problems that are associated with this residual HFO that these places tend to use. But those aren't the only problems. Because the HFO has such a inorganic content, you have certain inherent problems that are associated with that. Namely, if you have catalytic fines that are left over, those can cause damage. Those can cause wear to critical areas like fuel pumps, piston rings, cylinder liners, and over time, this means that this becomes somewhat of a maintenance issue, an expense, because you have an increased frequency of having to change injectors and overhaul these areas, and this takes money out of the maintenance budgets. And then, of course, HFO is associated with high temperature deposits, and also, you know, erosive damage of places like exhaust valves. So you got those, and then, of course, the list goes on. Fouling of turbocharger nozzle rings. Fouling of turbochargers is a considerable issue. Also, fouling and corrosion in the exhaust gas economizers. If you can have unsatisfactory emissions levels, which means pollution of the environment's an issue. And then if you get a situation where you're having to mix different fuels in the same storage tank, more of a logistics issue, well, sometimes you can get incompatibility issues where the fuels don't tend to want to mix as well as you might like. And so, listing off all of these problems from the last 3 slides, the question that comes to mind is, how much does each of these affect or cost the specific industry that you're in? How much do these individual problems cost you as an operator? That's a question that you really need to consider, because the answer to that will inform the urgency with which you need to consider solutions for any or all of these. So at this point, it should be pretty evident that users of marine fuel oil have a lot to contend with. Now let's look at a few of these issues a little bit more closely to understand why they happen and what causes them to happen. So let's start with the pre-combustion stuff. Pre-combustion considerations, which for our purposes are going to be mainly HFO, stability, and compatibility. Now, when we talk about stability, what we're referring to is the stability of something is the fueled or that thing's ability to resist change in its properties over time. Well, I was going to say over time and temperature, but it's really as a function of time and temperature. Basically, if you're talking about fuel stability, then you're talking about how well does that fuel resist changes to some of its key properties as you leave it, i.e. as time increases, and as temperature changes. So that's really what stability is. Now, when we talk about compatibility, we're talking about ability of 2 different kinds of fuels to remain stable in a blend when they're blended together. Now, the reason that we bring up stability and bring up compatibility is that instability and incompatibility for HFO, first of all, are problems that users have to reckon with. And second of all, both of those are related to the composition of the fuel, specifically the asphaltene presence in the fuel. Now, to make a long story short, a more stable fuel is going to have a high ratio of resins to asphaltenes. So the stability of a specific fuel is influenced by things in its composition. Now let's look at this a little bit more closely. Now, all petroleum, all crude oil contains some amount of asphaltene molecules. Now, we'll get into what asphaltenes are here in a minute, but basically they're really large, what we call macromolecules. They're large molecules with lots of carbons in them, and they have a pretty high, they have a high carbon to hydrogen ratio. Now, normally they exist in a stable form in the fuel. They exist as these little micelle structures, which micelle, just think like a spherical bubble. So they exist as these microscopic micelles in the fuel, and they're stable because there are other types of molecules in the crude oil that are called resins. And the presence of these natural resins actually stabilizes the asphaltenes, and they just kind of coexist in nice, happy harmony, which is why we say a stable fuel has a high ratio of resins to asphaltenes, because the resins stabilize the asphaltenes. Now, if you take that fuel and you process it, let's say you do vis braking, you do some other things. Well, the vis braking, which is the process basically where they heat it in a furnace, they lower its viscosity, and then they crack or break apart the large molecules into smaller ones for the purpose of getting more distillate fuel out of it. If they do that, on the one hand, they'll get more of the profitable distillate fuels out of it. They'll get more LPG, they'll get more gasoline, they'll get more number 2 diesel. However, that process destroys a lot of these resins that had served to keep the asphaltenes in a homogeneous suspension. And so when you kick out a residual fuel that has been processed in this way, or is left over from processing in this way, it is going to be inherently less stable than it was before, because there's nothing to keep the asphaltenes in natural suspension anymore. So that's why you get instability with heavy fuel oils. Now, these asphaltes, as you can see here, can be pretty large, complex molecules that might look or be represented something like this. The green are carbons or even benzene rings, and the white are hydrogens, and you've got some other things like nitrogens in here and oxygens in here. So asphaltenes are these very large, complex carbon-based molecules. Because they're large, that also means that they're heavy. And in addition, because they're large and heavy and contain lots of carbons, that means that if you burn them, they're going to provide a lot of heating value. So they are a significant contributor to the heating value of the heavy fuel oil. And now asphaltenes have been known about for more than a century, close to 2 centuries. They were really first discovered in the earlier 1800s. And they'll have a lot of carbons, they'll have a lot of hydrogens, oxygens. Typically, their molecular masses will be 400 to 1,500 units. So that's all ancillary stuff here. I'll give you a little bit of background. This is a micrograph picture of what agglomerated asphaltenes that are sticking together, what they might look like. Now, asphaltenes are a contributor, as we have implied, they're a contributing factor to the formation of sludge polymers. So when we talk about the fact that processed the HFO that has come from processed fuel will have asphaltenes that drop out of it. When we say that, at first you say, well, so what? But one of the implications is that these asphaltenes are a problem because they help participate in the formation of these really large polymer molecules that end up making sludge drop out. Now, a polymer, if you remember from science class, so all polymer really is just a big, large molecule that is made up of a bunch of smaller units that are bonded or strung together. The asphaltenes contribute to the formation of them because they help act as building blocks for some of these large polymers. And so if you recognize that as a problem, then you also have to recognize that one thing that might help solve this problem is that if you can get some kind of dispersant and you can put it into the fuel, and it will help to ameliorate or remediate this kind of problem. And so that have to start considering what would be the usefulness of doing something like that. Basically, you remember earlier we noted that the secondary refining processes, the processes like vis breaking and cracking, when they fundamentally change the fuel's makeup, they make it more prone to sludge formation. And so this creates an inherent need to use stabilizers and dispersants in order to take the place of those resins that were destroyed. And so if you have those in the HFO, they will help keep the asphaltene molecules apart and help keep them from growing larger and causing problems. So if you're able to treat the HFO with some kind of dispersant, then what you're going to get, the benefit that you're going to get, is you're going to decrease the amount of fuel sludge dropout that happens, and you're going to get, from a practical standpoint, you're going to get less blocking of filters, and you're going to get less sludge showing up in your centrifuges. And so all of those are good things. Talk about some other pre-combustion issues that HFO has, because as we progress in the discussion past the stability issues that marine HFO might have, we might need to start considering combustion-related issues, problems that happen pre-combustion, during combustion, and then post-combustion. So let's examine some other fuel-related problems with marine fuels on the pre-combustion side. They are, and this is a little bit of reiteration from an earlier slide. Excessive sludge precipitation, we've already covered that. filter blocking and water or centrifuge overload from sludge. We mentioned that as well, and we mentioned the fact that dispersants and stabilizers can help cut this down. The presence of catalytic fines in the fuel. Catalytic fines, we're talking about the leftover inorganic metallic content, and then those catalytic fines can cause damage and wear in areas of the internal combustion engine. And then, of course, partially stabilized or partially emulsified water can also be an issue as well. Now, fuel injector tip fouling, fuel atomization, abrasive wear. Again, we have mentioned those earlier as problems that marine HFO users have. Now, this schematic here, we put this up to show you that, first of all, there's a lot of different areas to the fuel transfer system, and mainly to show you that the fuel has to go through a number of places on its journey before it reaches here, before it reaches the place where it burns. And the reason why we show this is because it helps illustrate the fact that there are lots and lots of different areas where things like fuel sludge can cause a problem. So what do you have? Well, you start with a storage tank here that has a heater, because a lot of heavy fuels have to be heated in order to make them flowable. You've got transfer pumps, you've got a set tank, a separator pump, which can be affected by the catalytic fines. You've got another preheater. You've got the centrifuges to try and get some of that stuff out. Again, we mentioned that excess sludge will build up in here and cause problems. Then you've got the service tank. You've got flow meters, mixing tank. You've got pumps in different areas, different heaters in different areas. And then it eventually reaches the engine here. And so basically, excess sludge presence in that marine HFO can cause a problem in almost any of those areas. And the storage tank can look like, this is a marine HFO storage tank, and there was significant sludge presence in the bottom. I don't know how deep this goes, but the fact that it's so readily visible shows that there is a fairly significant amount of sludge in there. Now, remember, all of this sludge used to be in that HFO. So the fact that all of this dropped out means all of this energy value, all of these macromolecules are not being burned by the engine, and so whoever this tank belonged to is not getting the full value out of their heavy fuel oil that they paid for. It's lost heating value, and lost heating value is an economic loss. Same thing for filters too. If you got excess sludge presence, it comes out in the centrifuge. Again, remember, sludge is a problem because it's unstable, and so it's more likely, because it's not in homogeneous suspension with the HFO, it's more likely to be caught by the centrifuge and to be spun out of it. And if it's spun out by the centrifuges, then again, you've got lost heating value because it's not going to be burned as it should be, and so it is a potential economic loss because that customer's, again, not getting as much out of that fuel as they paid for. Is that you can have pre-combustion problems, viscosity controllers, fuel heaters, filters. You can have fouling of the fuel pumps, and a big one, deposit problems in the fuel injectors. Deposit problems in the fuel injectors are one of the more serious issues because the fuel injector is the thing that delivers the fuel into the combustion area, and not just delivers it into it, but delivers it in the optimal form that it will be optimally combusted. In other words, it atomizes it. The smaller the droplet of fuel, the better that fuel is going to burn. Today's fuel injectors, whether you're talking about the fuel injectors in a large marine engine or the fuel injectors on your car or truck, today's fuel injectors are very well designed to be able to deliver the fuel in the best way possible. But if you have it's valve injectors. If you have deposits that build up like on this one, if you have excessive carbonization like it does here, then that's not going to happen. And so you have subpar fuel delivery into the combustion zone, and you're not going to get that fuel's not going to burn as well as it should. So this illustration here, this is a fuel injector tip from a marine engine, and you can see this kind of starburst deposit, or what they might even call a cauliflower deposit. You know, the injector was not in good shape. So what do you do about all this? How do you what do you do to solve these kind of pre-combustion problems? Well, whatever you're considering, you're going to want to look for certain characteristics, such as it should be able to act as a stabilizer and a dispersant. It needs to stabilize existing asphaltene content in that fuel to kind of take the place of the resins that used to do that job function. And then it also needs to have a dispersant to be able to keep existing unstable asphaltenes apart. If you can keep those apart, you can keep them from sticking together and forming larger and larger molecules that eventually turn into sludge. So, first characteristic of a best practice solution, it needs to be a stabilizer and needs to be a dispersant. It should have the effect of improving the efficiency of both centrifuging and filtration. Again, if it has an effective stabilizer and if it has an effective dispersant, then it's also going to this. It's also going to do this, reduce fuel slop waste, save fuel. It's also going to improve the efficiency of centrifuging. Typically, stabilizers and dispersants will also help the injectors as well by enhancing the fuel oil atomization. So those characteristics, those effects, those are all things that you want ideally in something that you're considering to solve pre-combustion problems with marine HFO. Now, that's all pre-combustion problems. What about problems during combustion? Let's consider the kinds of combustion issues that HFO can have in internal combustion diesel engines, especially on the marine side. Now, in order to understand combustion problems with fuel, you have to better understand the combustion process itself. Now, the basics of combustion, and again, this might be relatively simple, but sometimes it's useful to go back to the basics. You know, the basics of combustion is that it yields heat energy plus water vapor and carbon dioxide. Now, how to achieve this to the best degree possible? Well, therein lies the rub. That's the riddle that we are always working to try and get to. Now, optimal combustion comes from what we call MATT. These are the F's of optimal combustion. M is proper mixture of the air and fuel. You need to have the proper you need to, when you inject the fuel into the combustion zone, it needs to be injected in such a way that it will best mix with the air that's already present. Atomization. You need to have the proper atomization of the fuel. Again, that goes back to the job function of the fuel injectors. The fuel injectors are engineered to atomize the fuel into as small droplets as is necessary to make them combust in an optimal manner. T, proper temperature. You need to have enough heat in the air and the fuel and in the combustion zone. And you need to provide the proper time. You do need a certain amount of time available for the combustion process to be completed in order for the whole process to come off in an optimal fashion. So if you're going to achieve optimal combustion, you need to have all of these elements working together. So what happens during combustion? Well, let's take an example of where you have a droplet of petroleum fuel oil, and it has been injected or it has been atomized in good proximity to the flame front in the combustion area. So what happens to it? Well, first thing that happens is that because it's pretty hot in there, because it's near the flame front, the droplet's going to start, it's going to start heating. It's going to be heated, and as it increases in temperature very rapidly, the volatile materials inside of that droplet are going to come to the surface, and they're actually going to start evaporating, and they're going to form almost like a vapor cloud around that droplet. So this fuel oil droplet has this little cloud of volatile material that used to be inside of it, has come to the surface and is now surrounded that droplet. Now, as you would expect, that vapor volatiles, they catch on fire. They catch on fire, they start to burn. And so because the cloud, because it was around the droplet, now the droplet is enveloped by a flame. And this flame continues until all of the volatiles are consumed, and some of the cracked products in here are also consumed. And eventually, it's going to burn everything that it can under whatever conditions are present. And so the flame is going to die away. And that ends stage number 2. Now, when that flame dies off, you still got some of that droplet left. What you've got is you've got a coke residue. Or a particle of coke, as they call it. And now that particle of coke still has carbon in it. It's still got significant carbon value, and so it is still going to continue burning. As it burns, it's going to burn up between 1400 and 1700 Kelvin. We don't really use the Kelvin that much. I don't recall what that equates to in centigrade, but it's going to glow. It's going to continue to burn. And at this point, what we call this a cenosphere. When that combustion is completed, when all of the carbon that is going to burn in here is finished combusting, what you have left over is called a cenosphere. Now, in summary, what you've got is you've got injection, and then you've got the start of ignition, or when that fuel catches on fire. That you have an ignition delay period. Then you have rapid combustion of the fuel because of those volatiles, if you remember. And because that fuel is combusting, what happens inside of the engine is you get a rise in pressure as well. That's going to be what helps drive the piston. You've got a rise in temperature. Then you've got, after the volatiles finish burning, you've got a steady combustion of the rest of the coke, the rest of the less volatile components of the fuel. And then an after burning period where whatever is going to burn out of the fuel under those specific conditions, whatever's going to burn will burn, and then what you got left over are the leftover partially burned spheres. Now, what kinds of things cause poor fuel combustion? What kind of things help contribute to less than optimal amounts of the fuel burning the way that it should? We have to ask this question because unfortunately a lot of HFO users do not get the most out of their fuel because one or more things contribute to the combustion of the fuel being less than optimal. And what are those things? Well, poor atomization of the fuel definitely will have an effect on how well it burns. Slow burning fuel. Slow burning fuel equals, when we say slow burning fuel, think fuel with poor combustion specifications. Having to increase the amount of excess air to improve combustion, that might help get you better combustion, but it will lead to other problems like greater acid production. And so if you have to do that, then you end up trading the problem of less efficiency for the problem of greater corrosion issues. Combustion problems that we see are fouling the piston and having deposits in areas that they're not supposed to be, premature piston ring failure, accelerated wear of the cylinder liners, mainly associated with either excess soot production from partially burned fuel or from those catalytic fines presence, the metallic presence. Fouling of the Scavenge airport and deposits underneath the piston. All things that can be seen by marine HFO users. What do these problems look like? They can, these are some visual examples of what some of these problems may look like. This is the top of this is a piston crown, and as you can see droplets of acid that have condensed on that piston crown and will undoubtedly cause corrosive wear over time. This piston here, look, this, I mean, it's fairly obvious to see what the fouling damage is on this piston. You can see where the surface of the mill is compromised. This is a fairly good example of what a serious piston fouling problem might look like. Scavenge port deposits. The scavenge, the area where exhaust gases are forced out of the cylinder. And if those exhaust gases have, let's say, excess acidic content, then you can get fouling and corrosive damage in the scavenge port. And so these kind of deposits here are related to the fuel's composition, because whatever material, whenever you have deposits in any area of the engine, whether it's a pre-combustion deposit, whether it's a deposit in the fuel injector, or whether it's a deposit, technically a post-combustion deposit like these are, they're always associated with fuel composition, because whatever material is being deposited would have had to have come from the fuel itself. So what are the options for addressing these kind of combustion problems? We already talked about pre-combustion problems, and we said basically what you look for is a dispersant and a stabilizer. Well, now let's look at combustion problems. What are the characteristics of a best practice? What should it be able to do? Well, be able to improve the combustion such that combustion gets completed earlier, and therefore you have less soot production and a longer burnout time. Should be able to enhance oxygen transport during that coke combustion stage. If it can do that, it will cut down on the amount of unburned carbon. It will cut down on those cenospheres that are formed. And it should also be able to clean fuel injectors, pistons, and valves, because those are essential elements of the combustion system. And if they are in the proper condition, then they will enable that combustion system to function properly. So what kinds of things can do these? Well, what we have found is that metallic or organometallic combustion catalysts can definitely accomplish some significant benefits in this regard. See, if you have the presence of unburned carbon, if you have unburned carbon or partially burned carbon, then that means the fuel is not being completely burned. Now, this has been a problem that has been around ever since petroleum has been used as a fuel. So for more than a century, petroleum chemists have been trying to figure out how can we make the fuel burn better. And I believe it was Dow Corning in the 1950s started doing research on organometallic treatments. Basically what they were looking at is they were looking at certain metals, and they were looking at this idea that if you can put certain metals in proximity to petroleum that's being burned, you can actually improve the combustion of that. And what they found, the research and the results of the research that they did in the 1950s showed pretty significantly that certain kinds of metals can act as catalysts. And not only that, but if you put two or more of those metals together, then they actually have a synergistic effect and will actually improve combustion by multiple times what each of those could do on their own. And so what the results of that research have led us to being able to blend organometallic combustion catalysts into fuel treatments, put those into marine HFO, and dramatically improve the combustion of marine HFO. So how do they work? Well, this is the point to say, how technical do we want to get? Because there, combustion chemistry can be a complex field, but at the same time, I don't think they would behoove us to get too technical. So we'll try and keep this explanation fairly simple. Basically, what these organometallic combustion catalysts do is they increase the number of reactive molecules, reactive radicals that are formed. If you have more reactive radicals, they are going to want to improve combustion by their presence. So the radicals, they have more OHs, they have more single oxygen atoms. What those basically do when they get around a fuel oil droplet, because remember, they came from the fuel oil because the metallic combustion catalyst was added to the fuel. So they're already in the fuel. When that fuel burned, they increase the amount of volatiles that come out of the droplet. Not only that, but they lower the activation energy for the combustion reaction. And this is a key point. This is probably the easiest thing to understand about how they work. You probably know that combustion is actually just a string of chain reaction of chemical reactions where carbon-to-carbon bonds are being broken. And when the carbon-to-carbon bonds are broken, then heat is produced. So that's combustion. Now, any chemical reaction, whether it's a combustion reaction or not, any chemical reaction needs a certain amount of energy at the beginning to help start the reaction. That's the activation energy. What these combustion catalysts do is they lower or lessen the amount of energy needed to do that. So if you have less energy needed, then the net effect that you'll get is that you will have more combustion reactions happening faster and earlier in the process. And that means that all the things being equal, you're going to get faster combustion and you're going to get more complete combustion. That is the name of the game here. And so in terms of when we're asking the question, what does a best practice solution look like? And we say a best practice solution should contain organometallic combustion catalysts. Well, the ATX MFA family of fuel oil treatments from Bell Performance are formulated to deliver these kind of combustion catalysts that are needed to solve these fuel problems. Here, what's the difference between fuel that's treated kind of combustion catalyst in ATX and fuel that's not? Remember we talked about the centrifuges. I wish that I had actually put these pictures earlier when we were talking about centrifuges, because this is an excellent visual representation of the before and after. See, on the left, this one here, this is essentially a soot particle. This is a soot centrifuge. And this is an electron microscope picture of it. And as you can see, it looks fairly solid. It's got a few holes in it, but by and large, it is a solid piece of unburned carbon in here. But when you add combustion catalysts, like the ones that are in ATX, and those combustion catalysts, remember, they increase the amount of volatiles that come out of the centrisphere, and they lower the energy of activation. They cause it to burn more completely. You're going to get something that looks like this. You can see this is really more just like a shell. There's significantly more carbon that has been combusted in this one than that is basically the difference, the kind of difference that combustion catalysts like the organometallics in ATX can do. So the combustion catalysts in the ATX marine formulations have an obvious and measurable effect on combustion. But a picture can only go so far. How measurable are their effects on combustion? Well, here, what you see is data that shows the difference in unburned carbon levels remaining after a defined combustion period. Now, what you've got untreated marine heavy fuel oil here, and it was combusted, and the amount of unburned carbon by mass or by weight was measured, and it came out to about let's say 1.35%, 1.35. They took the same heavy fuel oil treated it with an iron combustion catalyst, ran it through the same combustion process, and as you can see, there's significant reduction, over 60% reduction in unburned carbon, which means from here to here, the customer was getting all of this additional value out of their fuel. Same thing happened when they used the calcium combustion catalyst. They got about a 62.5% reduction. When they took iron and they added it to some kind of dispersant blend, that actually gave them a 66% reduction. Now, ATX, this specific product or formulation, which is designated ATX 1005 SSD, it actually has 4 different organometallic combustion catalysts. And when it's treated into the same kind of fuel oil, the reduction in unburned carbon was actually 88.2%, a very dramatic and very cost-effective reduction for the customer. So it's pretty obvious that using combustion catalysts in marine shipping fuel will give pretty positive benefits for the customer, including, of course, better fuel efficiency through more complete combustion. Now, post-combustion problems with marine heavy fuel, a big issue with that is corrosion. Typically, hot corrosion and cold corrosion are the 2 most predominant post-combustion problems that marine heavy fuel oil users have to face. Now, high temperature is a term that you hear a lot, and what it refers to the corrosion damage that occurs in the combustion zone, in the areas where the highest temperatures are, which typically are the areas that are closest to the combustion zone. Now, what are examples of a high temperature corrosion damage? Well, this is the top of the piston crown. Again, piston crown means it's in the high temperature area, and you can see the corrosive damage, compromising of the middle surface. Something's going to have to be done with this piston because the piston crown has been compromised by high temperature corrosion. Again, so picture what we saw a few minutes ago. See, again, corrosive damage on the top of this piston crown here. This damage is going to cost this shipping company time and expense to fix. Other areas of high temperature corrosion, it can occur on exhaust valves, it can on piston rings, as we saw earlier, it can occur on nozzle rings. It's basically anywhere that hot exhaust gases come in contact with. So why is high temperature corrosion fuel related? We said that earlier that deposits and corrosion came from were causally linked to constituents in the fuel. Why is that? Well, fuel composition primary causal contributor to high temperature corrosion problems, specifically because of the fact that marine heavy fuel oil contains certain inorganic constituents. It contains certain inorganics like sodium, contains calcium, iron, sulfur, and most importantly, vanadium. Now, when that fuel oil is combusted, these inorganics, they oxidize, they form oxide complexes like some of the ones that you see listed here. Now, these different complexes have different physical properties, including different melting point temperatures. Because some of them are high and some of them are low, then that means, depending on what the temperature is in the high temperature area, some of those may be solid and some of those may be liquid or semi-liquid. Which ones are more likely to be liquid? The ones that have the lowest melting points, like sodium vanadyl vanadate, or this one here, sodium vanadyl vanadate. If the temperature in that combustion zone is, let's say, 700 degrees centigrade, then this one, and this one, this one, this one, and this one are all going to be liquid deposits, whereas this one, and this one are going to be more solid. Now, these melting points matter because if they are liquid, they are more likely to be corrosive on the surfaces that they end up on. Here, you can see that the melting points of the different complexes depend on the ratio of vanadium and sodium that they contain. In other words, they are linked to the amount of vanadium and the amount of sodium that was in that fuel oil. Now, what you can see is, you see the y-axis is melting point temperature, and the x-axis is the ratio of vanadium to sodium. You start at 0.1, meaning there's more sodium than there is vanadium, and again, this is by weight. You get up to a 1-to-1 ratio here, then it continues to increase as you go up. Now, what you can see is that when there's less vanadium present, when the ratio is lower, then by and large in here, the melting point of the oxides that form from the combustion of that particular fuel oil are their higher temperature. They're, 1,000, 1,100, 1,200, almost 1,300 degrees. These ones are not the problem. These ones are going to be solid no matter where, and they're really not going to cause a problem. But when you start increasing the vanadium above, ratio of, let's say, 0.8 to 1, then suddenly the melting point plummets. And when you have melting points in here around, 600, 650 degrees C, these deposits here are extremely damaging, extremely corrosive, because they tend to be in a liquid form. So, melting point matters when it comes to corrosion damage, and melting point is causally linked to the amount of vanadium and amount of sodium content that's in the particular marine fuel oil that you're using. How do these corrosive deposits form? The basic mechanism to explain is, first step, the vanadium and the sodium are both oxidized, and they form things like V2O5 and Na2O. Those then act as essentially a surface substrate, as a sticky surface substrate, and they allow ash particles to build up on them. And while the existing fly ash particles are building up on the sticky surface, the sodium actually acts as a binding agent and actually makes them all stick together. The third thing that happens is that the vanadium and the sodium oxides start reacting with the metal on the metal surface. And they actually start fluxing with the magnetite on that surface, and they rapidly oxidize them, and they start corroding that surface. That's basically how it happens, and it is a very serious problem that really has to be solved. Marine operators really cannot afford to have their engines being destroyed by corrosive damage. So what are the best practices to combat this problem? Well, what it has been is that magnesium has traditionally been the solution for this, and for good reason. Magnesium is really good at doing the job of remediating this. What does magnesium do? Well, it does a number of different things. First thing it does is it acts as an ash modifier. It changes the physical properties, the melting points of the ash, and also what it does is neutralizes acid. If there's any SO3 that's in the air, it actually reacts with that and forms magnesium sulfate instead of allowing it to eventually form sulfuric acid. So both of these are extremely important for solving this kind of corrosion problem. And the industry has been using magnesium in this way for decades. So there's a lot of industry information on the amount of magnesium that needs to be used, don't go above this treat ratio, et cetera, very well known within the industry. Now, if you use the right amount of magnesium, you're going to have a substantial effect on those deposits. Let's say that you have V2O5 vanadate here. It has a melting point of 675 degrees. Do you add magnesium oxide to it? Magnesium oxide has a melting point of 2800 degrees. It will actually combine with this, and you'll get a new molecule, 3-MgO V2O5. And its melting point is almost 1200 degrees. This one is going to be a corrosive problem in your engine. This one is not going to be a corrosive problem in your engine. That's high temperature corrosion. What about low temperature corrosion? A pretty substantial problem. Some people call it cold end corrosion. Some people call it low temperature corrosion. Same thing. Both of those refer to the combination when SO3, sulfur trioxide, combines with existing water vapor and forms sulfuric acid. And then that sulfuric acid at some point will condense onto metal surfaces, and anytime you get acid condensing on the metal, you're going to get that metal's going to be destroyed. So the temperature at which this happens is the dew point. And anytime that you have a dew point that's high, if you have a higher dew point, then you're going to get condensation of this sulfuric acid vapor earlier, and you're going to get more corrosive damage. So the operator has a real problem here, because the operator does not want corrosive damage anywhere in his system. And you know, if you're in the industry, you already know pretty well. I mean, some of these pictures of examples of corrosive damage in different areas, you know, these are pretty serious. This one here is corrosion that happened in a turbocharger. You know, the turbocharger, of course, uses exhaust air, post-combustion exhaust air, helps use it to drive its machinery. If that exhaust air has sulfuric acid vapor in it, as it sometimes does, then that vapor is going to corrode and damage that turbocharger. And turbochargers are not cheap things to replace. This is an economizer, and this is, I mean, these are pretty serious examples of corrosive damage. You know, this is a heat exchanger device, and over time, acidic vapor in the air that was passing through it condensed onto its surfaces and pretty much destroyed that expensive piece of machinery. So the ship operator doesn't want cold end corrosion damage, but at the same time, they can't just snap their fingers and make it go away, because it's a balancing act. A lot of the things that they may think about to cut down on cold end or low temperature corrosion will adversely affect their combustion efficiency. So they take from one area to add to another. You know, the options that they typically would consider, the first thing that they would do is they would look at playing with their oxygen levels. You know, obviously combustion needs oxygen available in order to happen in the first place. If you have less oxygen available, you'll have less SO3 formed, and therefore less sulfuric acid, less corrosion problems. But you can't go too low on the oxygen, or you won't have enough oxygen supplied to optimally burn that fuel. So the operator has to find the happy medium with that. Another thing that they might do is they can try and play with the exhaust gas temperature. Again, we said that they want to keep the exhaust gas temperature above the acid dew point. Once it cools down to where it reaches the acid dew point of that particular system, that's when the acid is going to condense out. That's when they're going to have problems. So the solution for that is make the exhaust gas hotter. So it has basically longer to cool down before it theoretically reaches that dew point. But the problem is that if they make the exhaust gas hotter, they're basically losing efficiency because they're losing heat. The exhaust gas is carrying heat out of their system. So again, this is another area where they're having to figure out if they want to trade off efficiency in order to stave off corrosion problems. So there's no easy solution to this. If you do one thing, you might have an alternate problem. What areas are prone to corrosion damage? We already showed an economizer. We already saw a picture of turbocharger. We've seen pictures earlier for the low temperature corrosion. Typically, hot corrosive damage will happen in the areas of the system that are the hottest. So hot corrosive damage will be seen in exhaust valves. It will be seen in piston crowns. Also is seen in turbochargers, both the nozzle wings and the blades. Cold corrosion happens in the cooler areas. It can happen on piston crowns. I know we said piston crowns are susceptible mostly to hot, but it can also be susceptible to cold corrosion. Excuse me, exhaust valves. A lot of the exhaust trunking and post-combustion areas like the economizers, the funnel casing, valve casings. So the bottom line takeaway here, these are a lot of different areas, but the bottom line area is that corrosion affects a lot of different areas, and it's really something that if you're operating a ship on HFO, it's something that you have to be able to stay on top of. So remember when I mentioned an HFO combustion system had a lot of moving parts that interplay and interact with each other. Well, combustion catalysts are one of these parts. See, well, and more specifically what I mean is that if you improve combustion of that fuel by using something like a catalyst, if you improve combustion, then you will also have a beneficial effect on corrosion. So when an operator is trying to figure out how do I stay on top of this corrosion issue, remember we said that they'll use magnesium for that, but they can also use a corrosion improver, a combustion improver, combustion catalyst, and they'll not only improve their combustion efficiency, but it will also cut down on corrosion. It will have a dual effect. How is that? Well, basically, a combustion catalyst will be able to give them the same amount of combustion and heat output, but with less oxygen supplied. If they're supplying less oxygen, that means they have less SO3 that's formed because there's less oxygen to form it, which means less acid formed, which means less corrosion. Simple as that. And lower oxygen input basically means less air volume, which means they're going to have less heat loss because there's less volume of air, heated air leaving the combustion zone, and essentially less heat being lost. So a combustion catalyst, if you were to be able to combine that with an oil-soluble magnesium, then that's going to give the operator twice the value, and that is exactly what the ATX MFA products, that's exactly what they do. So for all of these problems that we've listed, the multiples that high-speed diesel engines have seen, what we recommend our ATX line of multifunction treatments. That's what we mean when we say MFA. ATX multifunction additives. They really do bring a lot of beneficial points for their users. They reduce unburned carbon deposits in the engine. They reduce engine wear. They improve both engine and system cleanliness, especially in the pre-combustion area. They're highly effective at reducing both low temperature and high temperature corrosion. So, reduce ash and carbon deposits in critical areas because of the magnesium that they contain. And the combustion catalysts that they contain reduce unburned carbon, and as we have shown, they improve the operator's flexibility for being able to maintain high levels of performance while also staying on top of those pretty serious corrosion problems. So the people that use ATX, they get less unburned carbon collected, which means they're using more, they're realizing a greater proportion of their fuel's energy value. They also have less sludge because ATX MFAs also contain those aforementioned dispersants, dispersants and surfactants, which means that over time, all of that sludge that normally had just stayed in the storage tank and had been lost, all of that heating value is regained and recaptured for the user. And so when you add all of this stuff up together, the ATX multifunction additives offer pretty excellent return on investments for the facilities that use HFO in diesel engines. So traditional ATX benefit or additional ATX benefits: stabilizes the fuel, reduces the formation of sludge, as we've seen, really helps the post-combustion emissions, disperses, eliminates water and moisture problems, and gives fuel savings because they're able to get more output relative to each unit of fuel that they're using. So Bell Performance, we really formulated the ATX line to try and be a complete solution, to give HFO using diesel engine operators, really give them everything that they need in one formula instead of having to consider multiple solutions. Typical application, or typical recommended dosage rather, starts at 1 to 3,000, but the actual dosage really depends on the fuel specifications. It will depend on the specific gravity of the fuel and also the vanadium and sodium content. If you have a higher vanadium content, higher sodium content, then the dosage can be a lot higher. It's very easy to apply. In fact, it's much easier to apply than traditional magnesium oxide slurries that had been used in previous decades. You can dose ATX directly into the settling tank. You can even do it by direct injection directly into the fuel line. You just have a fuel transfer pump that modulates the treat rate depending on the rate of fuel usage. So we at Bell Performance, we have been plating treatments for heavy fuel oil since the early 1950s, but that's not when we started. We actually, our claim to fame is that we invented the world's first fuel additive back in 1909. It was a fuel additive for gasoline for the Model T cars, and it was a detergent package. Since then, Robert Bell expanded his line into treatment of diesel fuel and HFO in the 1950s. And we have continually been formulating solutions for all types of fuels for pretty much since our inception. We sell both across the country and also we have significant international exposure, especially with the ATX line. We ship ATX to treat fuel oil in a number of different countries. Lots of countries, especially in the Far East, that use heavy fuel oil for their industrial processes and that use ATX to treat this. So the organometallics in the ATX, they are employed by all manner of HFO users, people who, all manner of power generation facilities, industrial, hospitals, and of course marine users. And really, all of these users, they're all seeking the same kind of solutions that you need, just specific to their own fuel. They all have the same goals. You ask anybody in any of these sectors what they want, they're all going to say some combination of the same thing. They're going to say, well, we want to save money. We want to reduce our fuel usage, if at all possible, while maintaining the output that we're already that we already have. We want to protect our machinery. In other words, we want to protect capital investment, make sure it doesn't get damaged. We want to recover lost fuel value, by getting more of that sludge back into the fuel to be burned. And this is especially important in the Far East. They want to be able to meet local or national environmental mandates as well. So they all have the same goals. And ATX MFA is really formulated to help all of them reach those goals. Who are these users? Who's been using ATX? Well, Northport Power Station, largest oil-fired electrical generation power station on the East Coast. It's based in Long Island. It's about, let's see, what's that, 375 by 4, let's say it's about 1,450 megawatts. Supplies about 25% of all the power for Long Island. And they have been using ATX since 2001. Now, we've said that ATX contains a lot of different things. It contains the oil-soluble magnesium and it contains the combustion improvers. They use it primarily for deposit control. They get the combustion improvers, but they actually don't even keep track of their fuel efficiency. The only thing that they want is they want to keep these clean. And so what that should tell you is how important it is for power generation HFO users to keep these clean and how effective ATX is at doing that. Tarbert Junction Station in Ireland, they've used it to keep them cleaner, to help with their soot blowing efficiencies, keep corrosion from damaging their boiler tubes, improve their heat transfer efficiencies, and typically they calculate that they realized a savings each year of close to $1 million a year, $946,000 a year. Other stations, Q Electric in Iki Island in Japan, diesel engine power generation facility supplying power for the island. They use ATX to reduce the acidic emissions that were causing a problem for the surrounding community. They used ATX. They saw acid emissions reduced by almost 30%, down to an acceptable level for the community. So it was a big public relations coup for them. Another customer in Japan, Kyushu Electric Tatsugo Oshima Island. Again, diesel engine power generation. Community was complaining about excessive soot production. They used ATX and saw a 12% reduction in large soot particle counts, 23% reduction in medium counts. When you get smaller soot particles, what that shows is that you're getting better combustion because more of that carbon is being burned. And that is what Electric realized. Other customers in Ireland, various industrial customers like soft drink plants, milling, concrete plants, typical fuels, they were the ones that were interested in fuel savings. And typically they would see between 3.8 and 5.3% fuel savings. MC Terminal reduced acid smut emissions by 20 to 50%. Various state hospitals in the state of Florida use ATX for over 10 years. Georgia Pacific, various customers in Taiwan, again, customers using ATX to help increase their output. Whether it was a plastics dyeing factory or a textile factory, they typically would report fuel savings of between 5 and 9%, along with a concurrent reduction in SOx and NOx emissions of between 10 and 50% per output unit. So, someone might say, okay, that's all well and good, and maybe I'd like to try ATX, but how can I tell if ATX is going to work for me? I mean, this is a question we have been asked over and over again, and typically when we recommend a test for a customer, we know that the customers want to reassure that this thing is going to meet their needs. And so if we're trying to prove or trying to build a case that ATX works for them, it's typically the best proof is going to be, it's going to be a combination of things. You're going to have some kind of controlled testing along with a concurrent or a complementary slate of customer experiences for customers that are similar enough to them that they can see those results and they can be convinced that they're applicable to their situation. So over the years, we've done controlled testing for ATX. We just ran through some customer experiences. But as far as controlled testing goes, there's things like when you're talking about emissions reductions, when you use ATX in high-speed engines. We tested it at the Engine Systems Development Center in Canada. It was a medium-speed diesel engine. It burned just regular diesel oil. And what they found after 12 hours of use, carbon monoxide reductions were on the order of 22 to 25%. NOx reduction, when everything was equalized out, NOx reduction went down of almost 8%. So there's controlled testing that gives supporting evidence of some good expected benefits that customers should expect to see in their specific system. Because testimonials, testimonially have value, but testing is probably what provides the most shall we say, the most real results. And that means testing in your specific system. It's one thing to say that Northport Power Station uses it and this customer over here uses it, but in the end, the most convincing thing is going to be if you use ATX in your specific system under your specific operating parameters and you see with your own eyes that it's giving a benefit. Now, when we're developing test protocols with people, one of the first things that we have to figure out is what is success going to look like for them, because success means different things to different customers, and it depends on what challenges they think they're trying to overcome. So thinking in your specific situation, what would be an attractive ROI for your situation? What would be an attractive ROI, return on investment, for your company? What are the challenges related to your HFO that you think that you're facing? If you were going to test ATX, you would need to know the kinds of parameters that could be measured accurately that would demonstrate that it was having a positive effect or even no effect at all. You would need to know how to measure success. And in our view, what we have found is that a successful test really is a win-win for everybody. That is why we always endeavor to try and collaborate with our potential customers to really come up with a test protocol that is most meaningful for them and will show them what they need to know, because if that test is successful, it's a win for them and it's a win for us. We get to provide solutions and the customer solves that problem or meets their challenge or achieves the substantial ROI that they needed to achieve. And so typically, together, a testing protocol will collaborate with the customer and we'll come to an agreement on what's the definition of success, what we're obligated to do, and what they're obligated to do. Typically, our obligations are more along the lines of we will supply the product at certain times and in the defined amounts. We'll get the product at the right time. We'll provide whatever technical support that they need, and we'll help interpret the results. And the obligations for the customer usually go along the lines of that they'll apply it in the agreed fashion, of course, because you can't run a test if you don't apply it. But then also the kinds of information that are going to be supplied. So we collaborate with the customer, and the good testing parameters are agreed upon. The typical length of test for an ATX test, it's not a short test. It's going to be typically 6 to 12 months. And definitions of success are typically influenced by what does the customer need to see happen. And we will typically ask for certain kinds of information to be supplied. What kind of information depends on what their capabilities are. What information do they usually track? You know, if the customer does not track emissions, does not measure emissions, we're probably not going to ask for emissions data, probably because it's not going to be important to them. But we'll ask for the necessary information to be supplied, and then we'll go from there. So wrapping this all up, we talked about a lot of different things. What we want, the case that we have been trying to make here, that hopefully we have done at least a semi-good job at doing. We really have been trying to demonstrate and to build a case that ATX fuel treatments for marine heavy fuel oils really have the potential to offer substantial benefits to you in multiple areas that your shipping business typically cares about. Fuel savings, deposit control, remediation of hot corrosion and cold corrosion damage, and then also recapturing of lost fuel value through sludge recapture, all of those things. So hopefully we have been able to at least pique your interest a little more and demonstrate to you through the various explanations that there really is something to this, and that, you know, no matter what sector you're in, we've been talking a lot about marine, but most of this stuff is applicable to other areas as well. So whether you're in marine heavy fuel oil use, or whether you're in power generation, whether you're in healthcare, industrial, any other facility that relies on heavy fuel oil, we will have tried to build a strong case that if you need a problem-solving fuel treatment for that HFO, that the ATX treatments from Bell Performance are going to be the right choice for you. Now, this brings us to our discussion here. We talked about a lot of things, and no doubt there may be some questions, some comments that you might have. My email is on the bottom of the slide here, ebjornstad@bellperformance.net. If you have any questions, then I encourage you to drop me a line. Send me an email at that email address. Reference that you were looking at the diesel engine power generation presentation. I will be very happy to help you in whatever way that I can. So thank you very much for joining me again. I am Eric Bjornstad with Bell Performance, Longwood, Florida. Thanks for joining me. See you next time.